I don't even know.
All right, guys, let's get the lecture started. Let's get the lecture started. Okay, so thanks for coming. So in today's lecture, we're gonna first talk a little bit about another implementation of the timer, SysTick. That's something we mentioned earlier in the lecture when we see the MVIC and when we talk about the interrupts and all those edge cases. We will put them all together to see how all those additional timers and different stack pointers and how do they work together. And then the main task for today will be the serial bus. We're going to move on to the communication protocol part of the lecture. It will take probably 2 to 3 lectures to finish. And before the class content, some announcement. Project ideation slides due tonight. So make sure you have those 3 slides, and then make sure you have the file names to be named after your unique name, so that you can get your points for that. Make sure you put 1 star on the top ideas you like. And we will have the team formation event tomorrow. This is the location and time, and it will be like Joe's Pizza and beverages served. So feel free to come check out. Well, you are supposed to come check out. At the beginning of that part, everyone just going to go on the stage, introduce yourself and your interest to the class. We will ask you to just speak. We will not let you use your ideation slides, so that we can keep the presentation going and keep more engaging, so that you don't just read from your slides. So you will talk to the entire class, probably like 30 seconds to 1 minute per person, and then we will kind of divide the classes into different clusters based on your interest. If you're interested in robotics or auto drive vehicles, etc. And then we will let you to organically form the team there. We enforce a team of 4 or 5, at least 4 people, so that we have enough slots in the end for the final expo and the meeting during the milestones. And for those who already have groups, still try to show up. It's a good chance to present your ideas and yourself to the class. And for those, if you form the group, after you form a group of 4 or 5, you can leave the event earlier. We will make a Google spreadsheet, keep tracking of all the teams that's already being formed. So if you have a team formed, or during the event, come talk to us. We will take the record, and then you can leave the event early. Any questions regarding the team formation for tomorrow's event or general final project teams? Yeah.
It's up to 5 people per team, right?
Up to 5, yeah, 4 or 5. So, unless in the end we have some odd numbers or something, then 4 to 5. Any other questions? Yes.
Is it on Gradescope, the project ideation stuff?
The Gradescope. So the Gradescope would just be posting the grades for that part. For the ideation slides, we have a submission folder on the assignment page. So if you click into that, there is a Google folder that we created, Google Drive folder, and that's where you should upload your ideation slides. Any other questions? Okay, cool. So this is the midterm distribution, and I think overall you guys did pretty decently. We will have the let me just get them all out. we will have the review request open until the 18th, so basically 1 week after we release the score. We have a mean around like 80, which is pretty decent, median 84, and standard deviation of like 14.6 or so. And yeah, this is the distribution. The exam is capped at 100, so if you, yeah, you will get 100 tops. Any questions regarding the exam? Distributions, scores, anything? You guys all happy with it? No question? Okay, that's pretty rare. So if there's no question regarding this, we're going to move on to the content of the class. So as we talked about, the first, we're going to talk about some of the edge cases that we kept mentioning in the previous lectures. So system timer, or SysTick. What it is, what does it do, and how can it be interacting with the rest of the program? Or is there like a different way? So before we dive into that, this is just to give you some like programming paradigms. This is what a typical like a code structure you probably so far has been interacting with. You know, we have like a one super loop, like a main loop, or like while one loop, so to speak. And then inside you have different tasks laid out in sequence. And you just keep the program or like the system just keep looping on this, and then you have a working embedded system that, you know, constantly responding to the outside input and output or whatever that's being determined to do, which is pretty nice. But then we talk about some of the limitation of this. For example, if you have if this list got like humongous, and then, you know, there's going to be like a bunch of delays on certain input signals or certain output signal that's supposed to come out at more or less more critical times. And to deal with that, we have introduced this interrupt, you know, basically a bunch of ISRs to help with the responsiveness. Basically, each of the peripherals have its own ISR number, so that whenever there's something needs to be triggered, it will raise that interrupt request, and then that request go to the MVIC. MVIC depends on the priority and the code running you know, mode, and then the MVIC will basically decide when the core will execute the ISRs, the interrupt service routing, basically the functions that each of these interrupt corresponding to. This works pretty nicely as long as these ISR calls are like very fast and very easy to execute. So every time you just have like ideally a few like tens of or like low hundreds of clock cycles, and then you're done with this task. So, you know, turns on switch up, turns on switch down, things like that. It works quite nicely. But I think when we talk about this, there are already being like questions in the class. You know, what if we need to do like a much bigger block of code within, you know, within this big loop, and those things are in its own schedule, right? What happens? How do we deal with that? The interrupt, the normal common interrupt with the peripheral interrupt signals will likely unable to cut that. So the way we do that is we do it through the called ROTAS. It's real-time operating system. So instead of having this one super loop that does every tasks in sequence, this one have each of the tasks laid it out in parallel, and each of the tasks can be executed based on its priority or based on its order. So how does this be implemented? You might feel, and this thing can work with ISRs together. You might be a little bit confusing, like, is this like real parallel, or it's just an implementation that simulates the parallel? It actually depends on what type of microcontrollers you have. If you have multi-cores, like say like a newer version of ESP32, I believe they have like what, 2 cores or something, then it could be actually parallel. So you could have 2 of these tasks implementing or executing at the same time. But for the majority, or for a lot of the MCUs, including the one that you work with during your lab, STM32, I believe they have like single core. But how do they still do this thing? So the idea behind this is that they implement in the software, kind of like the virtual timer, but in a different way. I think one of the classmates actually mentioned the SysTick in previous lectures. So what it does is they have a software implemented scheduler that's keep tracking on the list of these tasks, and it will keep track of what's the latest time each of these tasks are supposed to get executed. And whenever that time comes up for that task, the core will just switch to that task and then work on that. And then if there's no other task lying there, it's just going to stay in idle. If there is, it's going to switch to a different tasks. It might sound familiar with the interrupt, but they actually implement it differently. The reason for that is if we have multiple interrupts or pending, right? We have essentially one stack that keep tracking of all the previous informations. So when we pop back, we're still in the order of how we enter those stack, right? For this one, each task have its own allocated stack space. So for this one, you will be using that different stack pointer, the PSP, the process stack pointer. This one uses the main stack pointer. So for this one, each task have a task control block, TCB, and a memory that's allocated for it in SRAM for the stacking. And then it basically, whenever it needs to get to another task, the register value got pushed into the stack that task was allocated, so that it can just switch to another task, by popping back the value on the stack for that one. So they in a way, they're able to be dynamically ordered. Instead of the interrupts, normal interrupts, you have to be executed in sequence when you pop back or when you enter. This, you have the freedom of just randomly jumping inside each of the tasks. And how do they have the multiple stack locations? It's that they change the value, or in the task control block, they store its own PSP, like the process stack pointer address. So that value will be pushed into, that value will be loaded into the PSP register, so that the register or the core knows which location of the stack is supposed to look at to get all the values it needed for each task to execute. Okay, any questions regarding this? It might sound a little bit confusing, and I hope that by talking about this, we get a lot of these edge cases that in the previous lectures that we kind of just ignored to put them all together. So this will contain, like the different stack pointers that we used, and later on it will be with a few other things. But does this make sense? The overall, okay. Sorry, I think you first. Yeah.
In practice, do we have to implement this by ourselves, like the infinite loop? Or?
In practice, yes, you will need to implement for yourself. So this one, the while one loop, I think for a lot of IDEs, they kind of implement for you. But if you do with a little bit more lower level, you do have to. And for this one, it's going to be a bit more complicated. You will need to you will not only need to have each of the pieces of code, and you also have to figure out which part or how many space you need for each of the tasks and assign them so that they don't overflow or invade each other. So this one will be like a bit more complicated to do. But if you want to have like some more complicated system, this could be like one good way to go. There's no like strict good or bad between them. It really depends on your tasks. If most of these interrupts are just some short commands or short instructions, this will work probably very good. Like, could be even better than that. This one is so that if you have a bunch of tasks that needs to interrupt each other, and they need to be, then they contain a large set of instructions to run, so that running one of them might significantly delay other things in the pipeline, then this will be the configuration to go. Yeah.
I was confused because you said that each task had its own stack pointer, but then you also said that
it has its own stack pointer address, but they all got loaded into the same stack register. It just saved its own address.
I see. So you would pre-allocate memory space and then have them using different parts of it, and whatever task is currently running, that stack pointer will go in the PSP.
Yes. Yeah. Yeah.
On the real-time operating system side, each task in this sense is, because it has its own stack pointer and its own memory, in that sense, it is just a thread, right?
So they still share one stack pointer. It's just the value it's stored in that stack pointer register is keep changing.
Oh,
Yeah.
okay.
Any other questions regarding this? Also, this real-time operating, the real-time here, it's more stands for predictable. It's not like a guarantee that this will run faster than this or runs better. It's just like a guarantee on the predictability. What it actually does is, because it still have all those interrupts that can interrupt these parallel tasks. It's just the scheduler, which will be connected to the SysTick we will talk in a minute. The scheduler will keep tracking of what's the latest time this task has to be executed. And then when that time hits, it would trigger this task to be run. And it's totally possible that the system for a lot of time just within like an idle stage. Yeah.
Is that idle state that you're talking about, is it like lower power? Could you use this to?
Yeah, it could be like a lower power, exactly. Yeah, could be lower power, could be, I don't know, you have like a sleep function inside, just keep looping. Yeah, these are all possible. We go down this general structure of how the RTOS, the real-time operating system, works. Okay, cool. So what all that has to do with the system timer, or SysTick. Basically, what this is it generates an additional, like an interval, so to speak. So this SysTick will be connected to another clock. That clock is used actually by the AHBs, the high performance advanced peripheral bridge, which we'll talk in a second. But basically, it will have its like a fixed time intervals, usually have some sort of real-time reflections. So usually it corresponding to, say, like 1 millisecond or 1 microsecond. And that can be done by like prescalers. And we use this to just keep counting down. And whenever it hits 0, it will just check on all the tasks and see, any of the tasks needs to be reordered to be, have a higher priority to execute, etc. There are like different usage. The ones we mainly talk about is the RTOS, the real-time operating system. But it can also be used just for like the time delay functions. If you, in a lot of the code, you have like a sleep or delay with a number, that's usually done through the SysTick. And just to put everything together, from the previous diagrams we have, there was a piece of things that goes to NVIC that comes from the core. So the system timer comes from the core, and that gives the system tick IRQ. And that IRQ, just like any other interrupt request, has its own priority, which you can set, and then which also means that for those peripheral IRQs, when they all work together, you could have super high priority interrupts from the peripherals that interrupts the system tick, the SysTick interrupts. So they all work together. And what's the next instruction or tasks or handler function should be fetched into the core? Who will be the decider for that? The NVIC. So the NVIC will just decide, it have all those functions, all these requirements from different part of the system, different part on the chip, or even from outside of the chip if it's like one of the external device connected to the peripheral, and it determined based on the priorities and the timing, it will decide which one goes to the core. And when I say NVIC decides, that actually means the program, which is you, decides, because you are the one who's going to set all those things together. Yes?
What happens to the SysTick when you're either like setting up and you're still in the MSP mode, or if you're in the idle mode, would it still go off every millisecond?
Yeah, it will go off. Yeah, it just it might don't do anything.
Okay.
That's fine. Yeah, it might not do anything, but it's gonna keep. Yeah. Any other questions? Okay, cool. So from like if we look at the diagram of the SysTick, it's some type of clock comes down to a counter, and this counter happens to be a 24-bit counter, and it counts down only. It only counts down, but you can set what's the value that it starts to come down. So that's down to the reload value register, and whenever it reaches the 0, there is a SysTick ISR being triggered, and something might or might not happen. Depends on if there is something that needs to happen at that time. And to give you like a, just like a drawing, you know, if say we set it to, what's the value? 6, and then it just counted down all the way to 0. So that makes this, the whole time of these 6 plus 1 clock cycle, which is the 7 times the clock period. So that's the amount of time. If you set the reload value to 6, that's the amount of time each of these SysTick ISR is going to be triggered. And just like the other part, you know, like other interrupts, it has own registers for control. For example, this one, it controls like the stack. Oh, sorry, like the state of the SysTick. We have, say, like the count flag basically shows whether it's being counted to your 0, and then we have the clock source that we were talking a second. It will show which clock it's being connected to, usually to the high-speed clock that the AHB uses. And then is it enable and tick interval, etc. And another edge case, we left it out in the previous lecture, the AHB, you know, AHB versus APB. The main difference is one runs way faster than the other. I guess depends on what the way stands for, usually like in the magnitude of tens or even tens or hundreds, I guess. Yeah, usually tens or hundreds. And that's the clock. The AHB clock is the one that will be used usually by the SysTick. So you have a choice to choose whether use the direct outputs from that HB or through a additional prescaler. Usually in our system, the prescaler was set to be 8. So you can either just directly use that clock or use the HB clock divided by 8. Any guesses why it chose to use the HB clock rather than, say, APB clock? Yes? To what? To create a shorter interval, actually, to create like a finer interval, yes. And you also have the option to have more responsive system in case you want like a super fast system tick. Any question regarding this? Okay. And there are some other registers, the ones we talked about. We also have the reload value register, just the value that that will determine where it starts to counting down from on 24 bits, as we said. We have the current value register, just the name explains itself, and then we have a calibration register, which I think we can briefly talk about. So basically, what this thing tells you is the 10 ms is the number that's being used for what's the value you set for the interval. So essentially, what's if you in the system, it's currently set to this value, and then if you have a sys clock that sets to 50 megahertz, which is I believe what our board is doing, STM32, then you nicely have a interval from the SysTick to be 1 millisecond, I think. So that can decide what's the interval on each of these will be set it to. Usually, if it has a, if the skew basically means that if it's exact or an approximate. So if it's an exactly say if we have 50 megahertz and that number, then that happens to just divide it into 1 millisecond, then that's good. If it's not, then the skew bit will be a different value that indicates that the 1 millisecond in this case is like a small approximation. Could be like 1.05, 1.005 millisecond, rather than like a very precise 1 millisecond. Basically, it depends on if you can divide it without remainder. And the known reference basically means that whether this value have any real world time reference. So it's possible that this, it connects to a different clock source if you set it to be, and that clock doesn't have a real world. Maybe it's after a bunch of, implementations or some calculation. It doesn't have a very good correspondence to the real world. So it's not like a, so to speak, integer value of like a millisecond or second, then that non-reference flag will go up, so that you know that this is its own SysTick counting stuff, but we don't necessarily take this as the real world time to use in the system, but it will still count nevertheless. Yes.
So if I'm understanding correctly, this register would have perhaps a different value for a different Cortex M4 implementation.
Yes. So yeah, this can be decided by the predefined by the different chip designer, and those values are just happen to be the one value, the values that we the one we were using in our class, and it's nicely divided to be 1 millisecond for the interval. We good? Okay, perfect. So that would be the SysTick. I hope that kind of put everything together of all the edge cases that we talked about in the previous class. Yeah.
Can I just ask, like, what count flag and taking are? They were there in the diagram.
Which one?
Count flag and take in.
Let me show up this slide one more time. The count flag and ticking.
Yeah, at the bottom.
Oh, the ticking is it's the interrupt enable bit, so it enables this interrupt. And what's the other one? The tick. The count flag. The count flag is the whether it reaches 0. So the count flag, the count flag and tick enable, they go through a AND gate here. So if both of them are true, then there's a SysTick interrupt being triggered. So it's possible, if you're just doing that one super loop, you don't have to enable this. Then it wouldn't trigger a system interrupt. It wouldn't trigger a SysTick interrupt to the NVIC. Any other questions? Okay, perfect. Cool. So we're going to talk about the remaining of the class of talking about the communication buses. Generally, in the class, we're going to talk about these following four: the serial bus architecture, the UART. It's all of them are serial. The UART is one implementation of this, and for the next class or so, we're going to talk about probably the SPI and I2C, I2C, depending, however you want to call this. Let's start it with a serial bus architecture overview. So a bunch of pretty useful references if you want to dig really deep into this on like the reference menu, the official source for the chip. These are the chapters. You could check it out. I think they add together to be like 500 pages or something, but they are a good source for you. If you want something from the textbook, this is the chapter that you can reference to or read. And we have looked at a bunch of different communications or different buses within a chip, right? But what do we need to do to communicate between chips? So this is what, starting from this lecture, we're going to be mainly talk about. So previously, the APP bus, all those mainly like parallel communications within the chip. That's just for within the chip. And then and here, the within the chip part you can actually see in some of these. If we zoom in, I think we have a slide for that. So like these things are like the sometimes within the chip ones. Oh, sorry, that's actually okay. Forget about that. That's actually for outside the chip. But anyway, we're talking about how we're gonna interact between communicate between the chips in this lecture. When we design these communication buses, there are a few things that we generally will consider as hardware designers. First is the wiring. Basically, this will decide whether this communication between the chip are parallel or serial, meaning basically how many wires you need for each bit. And then the speed, depends on how you count it. You can count it by bits, bytes, words per second. But that's something we should also consider. And timing, is it supposed to be synchronized or asynchronized? Synchronized meaning they share the same clock source. So asynchronized meaning they have its own clock source, or even some that don't have its clock source. And number of destination and sources. Basically, how many chips talking to how many chips. We will talk a little bit more later, but usually we characterize them as like master devices and slave devices, and it could be like one master with a lot of slave devices, or multiple masters talking to multiple slave device, etc. It can also be bidirectional, so just depends on which communication protocol you end up implementing. And we have different ways for the arbitration. We have daisy chain, centralized, or distributed ways. The APB is one of the example of like, I guess in between of the centralized, and they have like a shared bus. We'll show this in more details. And then we have different, like when we talk about different protocols, that basically means like what data format is going through, including is it parallel or is it in serial. The data format and the redundancy, any of the say parity bits or any other mechanism used to make sure the data integrity. And first we would look at some example, like just how parallel works. Pretty straightforward, just like when we talked about doing the APB buses. One wire connects to, which basically depends on how many bits you need. One bit gets to its own wire that connects between the transmitter and receiver. And basically you will need multiple wires for that as well. Basically by design, this will be very good for high bandwidth transmissions between devices. And also you will have the downside of a lot of the it's going to be much more expensive wiring, as well as more pings or more current requirement, more power consumptions, basically. It is not uncommon that to have this for between chip communications. For example, this was the slides I was going to referring to. These things are actually parallel communication protocols that's used for between chip communication. And sometimes you will see the connector for those, something look like that, or something look at the top. So imagine if you have like external GPUs that you want to plug into your computer, and chances are those are using this parallel buses and cables to connect them. And the reason for that is because you need to be as fast as possible, and chances are they're designed to be very close to each other. So that actual cost for the wiring or some concerns for data corruptions during the long distance transmission is not a main concern for these cases. We have also the serial ones. These are basically one single wire that connecting between the transmitter and receiver that send the data bit by bit. And it's going to require some sort of like synchronizations between the transmitter and receiver. And sometimes they include the extra wires for the clock or like handshaking. meaning if it's a synchronized, they have additional wires for the clock to share between them. If it's asynchronized, they need some sort of like handshake agreement on, what's the clock cycle to use for encoding, and when they're not really encoding, for just read the data and send out the data. These things are good for relatively inexpensive or not super time critical tasks or communications, as well as they are very good for the long distance connections, like the wires the wires you use to plug into, if you still do that, plug into the like plug into the internet on the wall, or like USB cables you use. Those are all good examples of the serial protocol. Apart from that, we also have some like I2Cs or Ethernet with various different protocols. They are all using the serial communication, under the serial communication, which is also going to be the main communication protocols we talk about in our class for like between chip communications. Yeah, the reason for that is because parallels there's not too much to talk about. They use a lot of wires, so the implementation is pretty straightforward. They have their shared clock as well. You just clock. So, a real-world example for the serial buses, like we briefly mentioned. This is the USB communication or USB connector, USB port, however you call this. USB stands for, as you might guess it, Universal Serial Buses. So in actual wires, it basically has this, it has the ground. Yeah, that's one thing. They usually, you need the ground, otherwise it doesn't know what's the reference. And for the USB specifically, in order to make the whole communication more robust or increase the signal-to-noise ratios, instead of having one line that carries logic 1s and logic 0s, they actually have two lines. One carries the positive, one carries the negative. And on the receiving, the female connectors, what it reads is actually the difference between this two value. So it will read the positive data value minus the negative data value to just boost this communication, boost this signal, and then have it to make it more robust to the environment noises. And those are the two wires after you plug in actually going to be the one who does the data transmission. Generally speaking, if we consider which type of communication protocol to use, parallel versus serial, we do need to consider like encodings or like how you essentially prepare your data and how you interpret the data from the receiving side. You also consider the data transfer rate. If you need super high speed, you go with the parallel. If it's like a reasonable speed, you go with the serial. Cost of pings, wires, and then the error detections or corrections. Generally speaking, the parallel ones, you can go faster. If at the same clock speed, the parallel will be more error probing, so it's less likely that it has an error for that, as opposed to if we are using the same clock, the serial could have more higher chances for that. And for the data transfer rates, just to give you some references, these are some typical serial rate. I think nowadays the USBs can be like, what's it now? USB 4, 3, 4? Something like that. It's going to be much faster than this. The Ethernet can go up to 1 gigabytes per second. So when we talk about serial, it's not necessarily meaning that it's slow. It's still pretty darn fast if you want it to be. And for the parallel, it could be faster. You have the if you have those for example, the high-speed memory. This is also like an old version now. It can just achieve more than 10 gigabytes per second easily. but these parallel buses are usually in very close distance to the core or to the chips that it would communicate with. A few other things to consider: the length of the wire. The length basically means it's going to be some attenuations. How much the data's volume got degraded. So maybe you started out with 5 volts. After 20 meters, it became only, say, 3.3. So when the distance is long enough, it's possible that that value will not trigger a logic high on the receiving side. Also, there's noise and capacitance. So if you have, this is also one of the advantages of the serial. If you have, say, a bunch of high-speed parallel wires going side by side together for a long distance, they can have some overtalks between each other and corrupt the data bit between them. And the environment, noise and stuff. The current switching, it depends on if we switch to super fast, then it could have these spikes on the signal that can also that could also corrupt the data you're trying to transmit or damage the receiving side. So just things to consider when you're trying to set your speed. For if you want, you don't want it to be too fast, but you also don't want it to be too slow. And obviously the number and type of wires. And this is what a like synchronized versus asynchronized. So for the synchronized version, usually I have this. Obviously we have one wire for the data communication connecting the transmitter and receiver, and then we usually have additional wires to connect the clock together so that they have a shared clock source. That's what make them synchronized. And for the asynchronized one, then it saves that one clock signal, and it doesn't require that wire. And then they basically usually have some sort of agreement on, what's the start bit look like, and then what's the speed I should, start to clock on the inputting data stream. So chances are, basically it's by default staying idle, and then whenever the receiver side detects a starting bit, it will be ready and start to clock in the data. And then based on their agreement between them, they clock at a certain speed so that and so that it gets this correct data. And sometimes they have an additional bit for parity check, and then they have an ending bit so that the receiver side knows this block of data is down transmitting. And this one happens to be an ASCII number. Is that S or 5? S, I think. Any questions regarding this? Yeah.
For asynchronous comms, does the receiver sample on like the edge, or is it because it's listed in the diagram sampling in the middle of each like start and stop bit?
Mm-hmm.
How does it do that compared to like doing edge detection?
That's a great question. We'll talk about that in next slides. That's a great question. Yeah. Any? Yeah.
How do they agree on the about cycle or clock frequency when they are not like synchronized?
That's going to be dependent on you. So you, the programmer, will tell then, for you guys, what's the communication speed you should set. It's a baud rate. I think we're jumping a little bit ahead, but remember in the code, sometimes you write, this is the baud rate of something so that you can print out something to your USB, like a serial monitor, right? That's the number that you set for each of these serial communications, asynchronized ones. Yeah. The start bit and end bit, the start bit and stop bit, they are determined by the protocol. So each different type of protocol have its own configurations of the start and ending. We will talk one of the examples. It's called UART a little bit in the later part of the lecture. Like how they set their start and stop bit. Okay, so just give a little bit summary here. For the synchronized ones, need extra clock. and can be high speed if the delays are small, if they're close with a connected clock. And it's pretty common in the parallel scheme, but it's also doable in serial. Asynchronized, less wire, not much of a skew concerns, and then it's more common in the serial schemes for the serial type of communication. A few other things to just consider when you design your own or like determine which ones to use. You have the clock period and wire delays. You have the encoding of the timer and data information, whether you want to use handshake or connecting the clock wires in between, or like the power consumptions. If you have like additional, say, if you have a wire that used for synchronizing clock, then the wire is very long, then that's not a really good design choice, right? Because chances are this clock signal gonna get tunated during the transmission. Yeah.
How does skew occur on a like synchronous bus?
How does skew occur on the synchronized bus? It will be if the distance is very long for the clock. Normally, if it's like a reasonable distance, that should not be too much of a concern.
So is skew basically one clock ends up behind the other just because of propagation delay?
I think, yeah, you can think like that. May not be like a whole clock. It could be, maybe you are touching the edges or, yeah, but yeah. Yeah.
And I had a similar question. So with the synchronous bus, when you're sending the clock and the data over the wire, like the clock signal could reach later than it was sent, right?
It's possible, yeah.
Would the receiver just lock it in when it receives the rising clock edge?
The receiver will use the received clock edges to decide, yeah.
Okay, so hopefully they're all like delayed by the same amount, so it'll work the same.
Yes, yeah, chances are they use the same wire. Oh, good question. Yeah, good point. That's why on like PCB design, if you have multiple chip on the PCB, you always trying to have those parallel wires to go side by side so that they roughly have the same length. Good one, yeah. Yeah. Otherwise, chances are if it's a super fast clock, you might have these issues. Yeah. Any other questions? Okay. So where were we? Here. Okay. And we will talk about the number of devices communicating. There are various ways of this, as we briefly touched before. We have like single source to single source communication. It's like point to point. It's usually pretty cheap connections. We also have single source to multiple destinations, as well as multiple source to multiple destinations. There are some considerations if you want to choose either one of them. Usually the single to single are pretty straightforward, and then when you reach to the multiple sources to multiple sources, things become a little bit more complicated. We will talk on this multiple to multiple one a bit later, I think next lecture, when we talk about like I2Cs and stuff. But generally speaking, if you just draw them out, they have these various type of ways to communicate. Also, like multiple to multiple is not limited to just one way of doing that. It can also be either in a mesh or a tree, hybrid, different type of design. The bus one is the one that the APB uses. If you guys still remember, we have a shared APB bus that connects to all the peripherals and the core together. And the point-to-point is the most straightforward one. When we have the multiple of these sources, it's very important to keep track of or decide who talks when. Basically who gets to use which bus lane that connects within this communication map or communication mesh, however you call this. There are different ways of doing that. We have the daisy chain or token path. Basically, it connects everything together in like a connects everything. Basically, it will have the signal pushed to the next device, and if that signal or the data is meant for that device do something. If it's not, then it just passed down to the next device. So that's one straightforward way of implementing it. The downside for this is, you can have like delays in some of the communications because it always have to go through this deterministic order of devices. We also have like the centralized ones. So these are usually they all talk to this one bus arbiter, and then that will basically decide who gets to use all these communication buses at one, and then depends on how you implement it, priorities or who called it the first, and then that will just be able to manage to deliver the data to the corresponding devices. We also have the distributed one. So this one is like no clear central arbiters, and then it's common that I have like a set of wires just connecting them. There are various different ways to do that. In the previous one, we have, for example, the hybrid or the ring. They can all be considered as the distributed ones. And you usually have like a fixed priorities or like the fairness scheme, so that within that network, it knows which one talks first. Here are some popular serial protocols. The UART, which is going to be the first one that we talk about today. And then we have the I2C or I2C, depends how you pronounce it. It's developed by Philips. We have the SPI. It's developed by Motorola. They have different like communication speed you can go with. The SPI will be faster than I2C. And we also have Ethernet. These ones we're probably not going to be. The USBs and Bluetooth. Yeah, I think for the Bluetooth, if you're taking 473, they will have like a lab on how you would implement that. And the USB is, we just talked about. So these are some pretty popular, like some popular serial protocols that you are likely interacting on a daily basis. Any questions? Okay, I've been talking for a long time. How about I give you a question on this? Again, parallel versus serial buses. Why does ARM use a parallel bus architecture for the APBs and serial bus architecture for chip-to-chip communication? Let's spend like 1 minute with each other, and then we can discuss some of the answers you guys have. Seems like you guys reached some agreement between the groups. Who wants to share? What do you think is the reason why the ARM uses the serial for chip-to-chip communication? Any thoughts? Any guesses? Yeah. Longer distance. I think that is one of the concerns that they definitely take into considerations when designing this. If you have longer distance, then the parallel is just going to cost a lot of extra wires to do. But on the other hand, we also have PCB board that have multiple chips on them. So for those cases, the distance is not crazy, but for those cases, usually the ARM, at least for the ARM architecture, is still decide to use the serial communication rather than the parallel one. Any thoughts on why in that case they still chose the serial rather than parallel? Yeah.
Because it's complicated to deserialize and interpret and serialize data. It takes more hardware.
To interpret the serialized data, but that they would just input the parallel one, right? But they didn't. Did I get this right? So if the serial would take more effort to decode. So for the ease of design, wouldn't they just choose all parallel?
That could be one reason, is what I'm saying, yes.
Okay, I see, yeah.
Could it be that with parallel you have to pre-decide how many wires you're going to send? So different chips might want different wires, but with serial it's more customizable because you could just encode that in the header or something.
Mm-hmm. Yeah, that's probably one of the reasons as well, because serial gives you more, I think, more freedoms on what type of protocols you could put on them. I think the reasons you guys mentioned are all part of the considerations. Another considerations they have is just the limited I/O pings they have on the ICs. So not sure if you still remember this figure. We have the chip inside of this package, and the package goes to the IC package. Each of the pings then connects to the chip-to-chip communication, and it only have this amount of pings there. So if we use parallel design, then it's going to take a bunch of pings, which is just not that ideal, given that we only have limited number of pings for the microcontroller unit in general. Sounds good to you? Okay, so we talked about the serial bus architecture overview. Next, we're going to take a look at one of the specific communication protocol called UART, the Universal Asynchronized Receiver / Transmitter. Again, if you want to read for more details, these are some sources you can refer to. So what is UART, the Universal Asynchronized Receiver and Transmitter? Basically, it's a type of hardware that transmits from the parallel output from your chip to a serial one, and then clock to another chip. And it's commonly used in communication standards with these names. We don't have to remember often. We're not going to test you on this. But what important to remember is the speed of this protocol is configurable. You can choose what's the speed you have. If you remember if you guys play around with Arduinos, the default was 9600, and then you can go all the way to 115200, or even higher if you have if it's more powerful chip. So you can have a speed configuration for each of these UART pairs. You can also have the single level set for each of them as well. Little bit history. I think Western Digital, I don't really know that company, but they are the one who first came out or defined this protocol back in the 70s, and then those are the connectors that they had in a long time ago. So, however, they are still widely used today, even after 50 years. It's still going strong. And any guesses on why? Yeah.
You need 2 wires and ground.
2 wires and ground, yes. So it's super straightforward configurations. And sometimes the old-fashioned way is the better way, right? or usually it's used for like the single to single point communication. So there's not too much complications between them. So it just seems to work great so far. And this is one of the, I believe, widely popular connectors back in the day, but it's all, yeah. And for the voltage levels that we briefly mentioned, they have different levels you can set based on which standard you're using. So we have like for example, some of them have the logic ones to be, it can be wide range from 5 volt to 15 volt, and the negative to be the same, -5 to -15. So that give a pretty good data preserving. So basically the amplitude you have on each of the signal bit is much higher than if you just have one data line, rather than have the difference between the plus and minus. Usually they use the differential in the actual practice just for these reasons, to have like a larger signal amplitude. And each of these have its own maximum distance and their maximum speed based on which you chose. For 4,000 feet is pretty decent. I don't think I see any like parallel ones that can go, people do that. So yeah, pretty decent. And today we usually use it for like chip-to-chip communications, and then we configure it in the way that I think one of the classmates mentioned, just 3 wires on device 1 and device 2 each have its own TX, RX. TX is the transmit, RX is the receiver, and the ground connects to each other so that you know what is the logic high and logic low. Important thing here, make sure the TX of the device 1 connects to the RX of the device 2, and vice versa. Because this is from that device perspective, the signal I'm receiving is from the signal that's being sent from the other device. That's why remember that. I think every year we have students have this diagram wrong on the exam too, every year. So please. And sometimes, depends on if you use, because this UART is, asynchronized. We will next talk about how it's possible to just have 2 of these, wires connecting together and share the ground. How does the receiver knows, when to interpolate, when to start clocking the data, and clock data at the correct value. This is just some system diagrams on the board we have. And if we zoom in, that's the part where the UART will be at, and have its own TX-RX that can be connected to, whatever external devices you want to talk to. From a data frame or the data format, usually this is what a data looks like from for a UART communication. It has a start bit that goes to essentially logic low. By default, in idle state, it's always logic high. And you have 5, 6, 7, or 8 bit. You can choose your configurations, but that's the amount of bits that for each of the data sent to. And the reason they chose that is to match the ASCII numbers. And they have additional optional parity bit there, and then additional stop bit. So 1 or 2 bit depends on the configuration, or depend to just fill in the block basically. This is what it would look like if we have 6, 7, or 8 bit. Oh, sorry. Let me actually so now it comes to the important question here. How does they know whether one to latch data or clocking the data from the receiver with its own clock? And how if you don't know when the data will arrive? There are a pretty good analogy to solve this. Basically is, I don't know, you're pushing like the kids doing a swing, you don't know if it's when it's gonna come in, and you are blindfolded. I'm not sure if I like this analogy, but let's just roll with it. And then you just keep pushing, and then you're pushing it way faster than they possibly coming, and then chances are you get the first time it goes, and then because you also know what's the frequency of this kid's gonna coming back. So at that moment, you kind of know what's the next time you're gonna push. And to put it in more like technical perspective, this is actually what it does. So it just you just sample this. You just sample like this UART clock, meaning the clock from the devices itself, like the receiver side. You just sample this way faster than whatever you agreed on the baud rate or the communication rate between these two devices. I think in practice we do 16 clock cycles faster, and then so usually at the high, right? Whenever it has this first low edge, first logic low, which means the starting bit, and the UART clock, you will start to count 8 clock cycles, which is half of the size of this data transmitting speed, and then you clock the data there, and then every 16 cycles you clock another one. I think one of the classmates asked before, how do they know that it might, clock on the rising edge or, falling edge? This is how they just make sure that they don't, because they try to just clock in the middle of each of the bit. Does this make sense? Yeah, this will actually be quite useful as well if you have like long distance, synchronized one as well. If you like the clock is skewed, it's not like a perfect square. You have some meta stability in between. This is also one of the technique you could use. You clock in the middle of the bit instead of on the rising edge or falling edge, and then. You know how many bits it comes, and then at the end you clock on the ending bit, and then you know that's the portion of the data that's being received. There is some slight difference between baud rate and data rate. I'm just gonna put it out, but basically, if we say have like a baud rate of 9600, each of the frame of data have like a start bit, a data bit, stop bit. In this case, we just say there's no parity bit. The parity bit is one bit that shows that whether the data is like it's an odd odd ones or even ones. So that will give you like a quick sanity check on whether you get the correct data. The transmission of this bit, for this data is not going to be just divided by 8. It's actually going to be roughly divided by 10. So because each of this data is like 1 byte, so roughly. But yeah, there's a difference between like bit transmit rate versus the actual baud rate. And we just briefly talked about the error detection, the parity bit. If the total number of 1 bits in the data, it's going to be 1. If it's even, and it's going to be 0 otherwise. So they have like a quick sanity check on that. By the way, if you have, this is not going to prevent 100% of the errors. If you have like 2 bit of the data that's got messed up, then the parity bit is not going to be able to check it for you. But just by increasing 1 bit, you decrease the the possibility of a error data coming without notice by a margin. So this is an example of of how the data comes in, and you will see that it stays at high, and then whenever it starts to have this start bit signal, which is a logic 0, and then on the receiver side it starts to log it at the middle of each bit. So this one 0, and then that's 1, 2 zeros, and all the way to the stop bit. And they can have multiple of these data streaming coming in, because imagine you're sending a word or sentence. Each of this transmission, or like the data frame consists of one character, basically, from the ASCII table. So it's going to have a bunch of them coming with very short time gap in between. And the way we would decide that is just checking on the start bit and checking on the stop bit. In this particular case, there is no parity bit, so the stop bit have the, yes. Oh, by the way, also the least significant bit or most significant bit, those two things, it's all decided by you. So you can decide whether the least significant bit comes in first or the most significant bit comes first. There's no like strict rules on that. For receiving data, it's pretty straightforward. Basically, you have receiving and sending. You have the data comes in, and whenever there is a start bit triggering, then you need to clock in the data, and whenever that data is filled in the register, it raises a ISR. If it's the core, it raises an ISR, and then the core know that there's some data ready, and then you can go just read it. And chances are we're going to have a bunch of these frames data come in, right? And it's whenever there's like a UART send triggered, because it's usually like a string, and then it's going to just start sending the first byte and do a quick like interrupt, and then send the second and the third. And usually this is done just in, hope you guys still remember, it's just the core, the processor always stuck in the handler mode. It doesn't do down stacking, so that it just do a bunch of the interrupt handler calls for that one interrupt referral. And then once you finish that string of sending, it go back to the normal processing mode, thread mode. It might look like a lot, but in real life, this thing take very small amount of time to do, which is also you shouldn't send essays in any of these. You should send like something quick, some strings, numbers. Don't send essays. And I think for the board you guys have, or most of the board, I think nowadays you probably have its own USB to serial module embedded in your PCB board already. But if you have like a bare chip to work with, you will need to connect an additional like a serial USB to serial UART module. What it does is basically it connects to the USB interface and then sorted all that data into a TXRX communication, and then from that chip it talks to your own microcontroller's chip. I think I had an image for that, but yeah. This is just an example of how this will be implemented. And similarly for the Bluetooth, so if it's a additional Bluetooth module that you connect to your microcontroller, I think you guys are going to work with one of the HM families. If that's the case, then chances are, or you could implement them through the UART protocol to your chip. So the data got sent first through the serial to the Bluetooth, and the Bluetooth does its wireless communication protocol to another Bluetooth, and that Bluetooth receive the data and then pass it to the other microcontroller, let's say another microcontroller, through the UART protocol. And for the there are some newer MCUs, for example, ESP32. ESP32 have its own integrated Bluetooth BLE modules. In that case, I don't think they use the UART within the chip, but you will notice that that Bluetooth transmission is going to be way faster than you can achieve on the STM32 with the HM families you connected with. That's the reason. The reason for that is because there is this additional layer of UART communication between your chip and the Bluetooth module. That's kind of slowing things down. So the Bluetooth, even if you go with like Bluetooth 5.0, you might not achieve the speed you would like to achieve. Any questions so far? Oh, we're doing great. So On the board specifically, we have, these are the amount of UART modules available to you. There are 3 multi-purpose. It's called UART. The S stands for synchronized. So in the board, we have that UART port can do both synchronized and asynchronized. We have 2 like the common UART modules on the board. And 1 LP UART basically means low power. That can be used, for example, when the device is in sleep mode or like ultra low power mode. That can be the signal to trigger like a wake up signal to the system. So we can save on energies and have the device to run for a long time. And each of these UART module have its the designated IRQ lines, so that whenever there's a data that come in or the data that needs to come out, there is going to be that one interrupt signal that's been pulled up to the core. Quick summary here: some of the pros and cons for the UART. The pros here: only 2 wires. No clock signal is necessary to be shared, and it has a one parity bit to allow for some error checking. Works pretty decently actually. So yeah, just think about if the chances that you have 2 bits of data wrong, and that data still came out as the data. That's pretty low chance. And the cons is the size of data frame, meaning every time of this, you can at most stand a maximum of 9 bits, and then it doesn't really easily support multiple peripherals. So the example we give is like single to single communications, right? The UART would be pretty hard or pretty complicated to achieve multiple sources talking to each other. And they have to have this agreed upon baud rate and data frame as the prior. So you have to decide this before you start the communication. And usually it's not common to change during the communication. And the internal clocks for both devices needs to be accurate and stable. Otherwise, because this basically entirely depends on how well your clock is when you're trying to clock in data. It has to be stable. Otherwise, you're gonna get some gibberish data. All right, I think we are at perfect time. So if you have any questions regarding any of these content, please come to me. If you have any questions regarding the exam, come to one of the open labs and discuss to see if you are able to get some points back. See you tomorrow.